Hello students, good morning everyone. Good morning Nana, good morning. Good morning Shankar, good morning Yogashri. Good morning guys. Welcome to the physics session. Inform others to join the session quickly Nana. Inform the others to join quickly. Right. Still joining. So guys, are you getting my voice clearly? Respond. Voice is audible. Is my voice audible? Good morning Raya, good morning. Is my voice audible? If yes, drop a message that yes it is audible. Yes guys. Right, in today's session, okay guys, let us go ahead now. In today's session we will be discussing about collisions. I have discussed one-dimensional collisions and numericals in the previous sessions, specifically elastic collisions. And inelastic, as part of inelastic collision also we have discussed perfectly inelastic collision, and as part of these collisions we'll discuss few more points. As part of these collisions we'll discuss few more additional points. So write down the subheading. First we'll see one dimensional elastic collision. Inelastic, not elastic. One dimensional inelastic collision. One dimensional inelastic collision. Yes, no, no. Good morning everyone. Yes, thank you guys. So voice is audible. Okay, thank you, thank you. Yes, good morning everyone. Good morning Kita Puja, Vagmi, everyone. Good morning everyone. Inform others to join fast. Still many have not joined. Yeah. What is that? One dimensional inelastic collision. Intake. One dimensional. One dimensional inelastic collision. Okay. So one dimensional inelastic collision. So as part of this, we'll see few points again. Inelastic collision. We know already what is elastic and inelastic collision, right? A collision in which both momentum and energy, especially kinetic energy conserves before and after collision is called elastic collision. Inelastic collision means the collision in which only momentum conserves but not the kinetic energy is called inelastic collision. One dimensional. What is one dimensional collision? I have classified these collisions based on different parameters, right? Excuse me, guys. Right. So, yeah, as inelastic collision, the collision in which only momentum is conserved but not the kinetic energy. It's called inelastic collision. In such inelastic collision, how to find the final velocities, and as a kinetic energy in elastic collision is not conserved, how to find the loss of kinetic energy, change in kinetic energy or loss of kinetic energy. Kinetic energy is not conserving means initially it will be having more kinetic energy, after collision it will have less. That means it will loses initial kinetic energy a part due to the collision or in the form of sound energy, heat energy, etc. Right? How to find this loss of kinetic energy, and especially sometimes we will be asked to find how to find the fractional kinetic energies also when comparing with initial kinetic energy. So these kind of things, so let us try to understand with the help of some examples. With the help of some examples, one of the example here we will discuss is what you call ballistic pendulum. By considering the case of our example of ballistic pendulum, we'll try to understand few more points, additional points here. Yes, let us see here, and for that uh, we'll try to find first we'll try to see how to find the loss of kinetic energy in a perfectly inelastic collision. So I will give you a brief derivation here, but actually the same thing, uh, what do you call it, the loss of kinetic energy in case of normal inelastic collision, it will be little lengthy one and a little complex related stuff. So it is not there in the portion that the derivations part we no need to worry about. Okay, for understanding purpose, how to find loss of kinetic energy specifically in case of perfectly inelastic collision I will explain. Then we will try to take consider the direct formulae related to inelastic collision or partially inelastic collision. Okay, first write down the subheading loss of kinetic energy of, under this, let this once again write down loss of loss of kinetic energy of perfectly inelastic collision, perfectly inelastic collision, a loss of kinetic energy of perfectly inelastic collision. Okay, right. So first of all, we know what is inelastic collision, right? Perfectly inelastic collision. What is perfectly inelastic collision? If you have two bodies of masses m1 and m2, and if they are moving with initial velocities, if they are moving with initial velocities u1 and u2 before collision, after collision they will stick together and move with a common velocity, both m1 and m2. This kind of collision is called perfectly inelastic collision. In such collision, this is after collision. This kind of collision is called perfectly inelastic collision. In this collision, how to find the loss of kinetic energy? Let us see. How to find the loss of kinetic energy? How to find the loss of kinetic energy? Okay. So to find this, let us try to first apply what you call. So you can say directly loss of kinetic energy is equal to the initial kinetic energy Ki minus final kinetic energy Kf. Initial kinetic energy minus final kinetic energy is loss of kinetic energy. Let us take this as equation 1, where initial kinetic energy of the system, we have to say actually Ki, Ki or Ki also, right? Initial kinetic energy of the system is half kinetic energy of the first particle plus kinetic energy of the second particle, that is half m1 u1 square plus half m2 u2 square gives initial kinetic energy of the system before collision. Whereas final kinetic energy is Ke final is equal to, after collision, both the bodies are moving together at the common velocity. So half to m1 plus m2 into v square. This is final kinetic energy. So difference between this will give you, try to find v here. V is equal to, in perfectly inelastic collision, from law of conservation of momentum, you have to remember that. You have to remember u1 plus m2 u2 divided by m1 plus m2, common velocity of after collision in perfectly elastic collision is this. And substituting this, you can write this as half into m1 plus m2 into v square, means this entire thing whole square, that is m1 u1 square, m1 u1 whole square Write it down as m1 u1 plus m2 u2 whole square divided by m1 plus m2 whole square. Here one m1 plus m2 gets cancelled, then you will get this as final kinetic energy is equal to half into here m1 plus m2, an extra term will be here in the what you call denominator. Otherwise you can write it as half into m1 u1 plus m2 u2 whole square divided by m1 plus m2 whole square. Oh, sorry, only one m1 plus m2 will be there, right? This whole square by this is final kinetic energy. This is final kinetic energy. Okay, so if you substitute this initial and final kinetic energies in equation 1, we get loss of kinetic energy. Loss of kinetic energy can be, here only you can write loss of kinetic energy, which is equal to delta Ke, which is equal to initial kinetic energy minus final kinetic energy. If you take this as equation 1, this is 2, this is 3, then by substituting 2 and 3 in 1, you will get loss of kinetic energy. How to find that? Let us see here. So note down this derivation, everyone. Try to write down along with me. Try to write down along with me, so that finish it fast quickly, then we can work out few numericals as well. So here we can express this as this implies what is that? Loss of kinetic energy is equation 1 implies delta Ke is equal to Ke initial minus Ke final u1 square plus half m2 u2 square minus final kinetic energy is this. So it is minus half into m1 u1 square. You see here m1 u1 plus m2 u2 whole square by m1 m1 square u1 square plus m2 square u2 square plus 2ab 2 into m1 m2 u1 u2 divided by m1 plus m2. This is the term. So this again, by cross multiplying this term with this, you will get next little bigger relation will get. Giribalaji, Haribalaji, Shubhan, Gunashilan, Sachin, Adhav, guys. So try to inform these guys to join the session and all. These points will not be repeated again. Of course, you can go through this session, but try to save the time. Try to save the time. Yes, inform the others. Inform the others to join the session. Right. Okay, it is equal to what? So on simplifying this, so if you multiply this term with the m1 and again this term with m2, this term with m1 and this term with m2, then if you simplify, you can write off, you can take it out, then on simplifying this by m1 plus m2 will come out, I mean in denominator, so you can write it as half into you can write it as m1 into m1 square, half you take this out, m1 square u1 square plus m1 m2 u1 square m1 m2 u1 square plus m2 m1 or m1 m2 only m1 m2 u2 square u1 square plus m1 square u1 square minus m2 square u2 square plus m2 square u2 square gets cancelled. So it is minus, what did you get here? Minus 2 m1 m2 minus 2 m1 m2 uh, and this m1 u m1 m2 u1 square m1 m2 u2 square you will get, right? So if you observe this again here, m1 m2 will be m1 m2 will be common. So this further you can write it as this is equal to 1 by 2 into m1 plus m2 into here m1 m2 if you take this out, m1 m2 if you take this out, again u1 square plus minus 2 u1 u2, it will be in the form of a square plus b square minus 2ab form. So you can write it as a minus b whole square, that is u1 minus u2 whole square, right? In this way you can write. Now this simplifying further you will get delta ke, loss of kinetic energy, can be expressed as, oh okay Nana. Okay Shubhan, okay Nana. Very good, very good. So because just you have not responded, I thought you are not there. Okay, so try to copy these points everyone. If you are not clear about any points, let me know so quickly. So this is equal to, therefore delta ke, loss of kinetic energy, is equal to how can you mention this, half into mass term, that is m1 m2 divided by m1 plus m2 into velocity term square is u1 minus u2 whole square. This is the expression for loss of kinetic energy in a perfectly inelastic collision. Perfectly inelastic collision. Okay, perfectly inelastic collision. Note down this everyone. This expression you have to remember, guys. As when the two bodies are moving in same direction and they stick together and moving with a common velocity, then loss of kinetic energy is this. Whereas here itself, write down one more additional point as a note. If two bodies are approaching each other and undergoes perfectly elastic collision, then loss of kinetic energy of the system. If in each other, two bodies approaching each other, if two bodies approaching each other and undergoes perfectly inelastic collision and and undergoes and undergoes and undergoes inelastic inelastic collision, then kinetic energy of the system is given by, when they're approaching each other means when they're moving in opposite directions, so you will consider the velocities. When they're moving in same direction, velocities will the relative velocity you can consider it as a difference between them. When they're moving in opposite directions, the velocity term will come as sum of these terms, or here actually get, instead of negative term we get positive term, that's it. Okay, so because here vector form if you consider we get uh, positive term, so and hence directly let me write this, then loss of kinetic energy can be expressed as delta ke, and here it is observed to be maximum kinetic energy may loss, and it is given by delta ke maximum, which is equal to half into m1 m2 divided by m1 plus m2 into u1 plus u2 whole square, u1 plus u2 whole square. This will be the loss of kinetic energy in this case, provided it is a perfectly inelastic collision only. Whereas if the collision is partially inelastic, that means coefficient of restitution you have to consider. In such case it is very complex to find the loss of kinetic energy, but in such case usually we come across the calculation of final velocities after collision. So let us try to write that also as a point. So write down, if two bodies if two bodies collide inelastically, then the velocities after collision are given by not perfectly inelastically, just partially inelastically. So that's why you simply will say inelastically. Then velocities after collision are given by, so write down this. Next, second point. Here also we are not discussing the derivation of this. This is little lengthy one. So directly I am giving you the expressions. Okay. The velocities. What is that? The final velocities. The final. Try to mention one subheading. Then you can write down. Then only it will be clear for you. Otherwise you may confuse. So write down like a subheading. Collision in a in a partially inelastic collision. Final velocities. Final velocities. I'm not done this. Use this one. Final velocities. Velocities after collision. After collision in partially inelastic collision. In partially inelastic collision. Partially inelastic collision. Partially inelastic collision means usually we call it as inelastic. Why you are using this word here partially? Because we have just now we have discussed perfectly inelastic collision. Okay, to distinguish between these two, we are using this word. Final velocities after collision in partially inelastic collision or simply inelastic collision. Okay, are given by. So write down these expressions. Write down these expressions. Directly, I am giving you the expressions, guys. Okay, the derivations we will not discuss here. So V1 is equal to V1 is equal to M1 minus EM2 divided by total mass into U1 plus 1 plus E into M2 divided by total mass. M1 plus M2 into U2, and V2 is given by V2 is equal to, I already told her, it is something like M1, in place of M1 minus M2 we are taking M1 minus EM2. In place of 2M2 we are taking 1 plus E. 1 plus E. The same term comes here, and this difference term comes here. So remember that. So here 1 plus E instead of M2 we will get M1. That is U1 term. So 1 plus E into M1 divided by total mass. Total mass M1 plus M2 into U1 term plus difference between masses. Here for V2, M2 minus M1 you will got in you have used in elastic. Here, yeah, instead of M2 minus M1, you have to use M2 minus EM1. M2 minus EM1 divided by total mass. Total mass M1 plus M2 into U2. This is U2 term. So these are the expressions for final velocities. These are the expressions for final velocities in partially inelastic or inelastic collisions. Whenever you come across inelastic collisions, you have to use these expressions to find the final velocities. Here we can discuss one special case also as a special case. Special case. Case 1 is if the bodies are identical, if M1 is equal to M2 is equal to M, and provided, and the second body is at rest, then, and if they are undergoing what you call inelastic collision, partial inelastic collision or inelastic collision, then the final velocities after collision are given by V1 is equal to V1 as M1 equal to M2, M1 is equal to M2, right, and U2 is 0, U2 term will become 0, this will become 0, then M1 equal to M2 means this both will be M, so M minus EM by 2M, so M, if you take it out it M cancel, then we'll get 1 minus E by 2, so directly I am writing here, right, 1 minus 1 minus E into 1 minus E by 2 into U1 or into U by 2 also, U1 by 2 also you can write 1 minus E by 2 into U1 will be your V1, and V2 is equal to, again U2 term will become 0 because U2 is 0 here, this will become 0, this becomes 1 plus E into M by 2M. MM gets cancelled. So 1 plus E by 2 into U1 will get 1 plus E by 2 into our special ballistic pendulum cases. I will give you this general description here. You may come across different kinds of questions based on this kind of questions. While doing numericals, we'll understand that. But how to deal with this kind of concepts, I'll down next subheading ballistic pendulum. Write down subheading ballistic pendulum. Write down, guys. Write down ballistic pendulum. I hope you have copied these points. Note down quickly. What is this subheading you have taken here? Final velocities after collision in partially inelastic collision. They are given by this. Okay. Next, write ballistic pendulum. Ballistic pendulum. Ballistic pendulum is. We have discussed some of the examples for perfectly inelastic collisions, right? Perfectly inelastic collisions. This is based on a perfectly inelastic collision. Okay, and in this case, we will discuss few interesting points. We'll see what are those. First, you should know what is this ballistic pendulum means. Okay, so it is in this simple. It is something like simple pendulum only. In simple pendulum, we'll be having a pendulum which a thread. One of the ends is attached to a rigid support, and another end is attached to a bob of mass. Here, it is same. The same thing. The bob of mass will attach here instead of what you call steel bob or something like we used to consider a wooden block of mass m will be attached at the free end of the string. A wooden block will be attached in case of ballistic pendulum. Okay, and we will consider the length of the string as l. Length of the string as l. Now the ballistic pendulum consists of a combination of this wooden pendulum plus bullet together will be called as ballistic pendulum case here. So if a bullet of mass m is fired horizontally onto the block with velocity u, then if the bullet gets embedded in the block, if the bullet gets embedded into the block, let me just give you the diagram so that you can understand this while discussing these points. If you have a rigid support and we have a block, this is a wooden block of mass capital M, let us consider, and if you have a small bullet of mass small m, if it is fired with velocity u, as or you can say that its initial velocity, this is a system of two particles, bullet and block system actually, and if it is fired with the initial velocity u, provided the initial velocity of this u2 is 0, then after this gets embedded, it strikes this, it gets embedded into this, then it will raises to some height, guys. It will raises to some height, so that this if you consider the string of length l, it will try to move up, so that this will move through an angle theta at this position, at this position at this position. When it is here, you can say this has raised, having mass m, this is said to be raised from this horizontal level to a height h. That means before collision it is at rest and it is moving. Just after collision both will stick together and they are moving. Oh, that is one condition. Then again, so here the final velocity of the system together can be calculated if we are asked to find this. But here one additional point also we'll discuss. After collision, now bullet and block together will be moving with some velocity, common velocity v. That means this system will be having some energy called kinetic energy. And after some, so here you can observe what was the initial kinetic energy and final kinetic energy, and hence you may ask to find the what is loss of kinetic energy of the system also. Loss of kinetic energy. Loss of kinetic energy is initial kinetic energy of the system and minus final kinetic energy of the system. Okay, so let us try to find the loss of kinetic energy in this case. Loss of kinetic energy in this case. Right. For that purpose, we will follow a few steps. What are those steps? Let us see here. First, you can take ballistic in case of ballistic pendulum and loss of kinetic energy. Ballistic pendulum and loss of kinetic energy. That means how to find the loss of kinetic energy in case of ballistic pendulum is the uh, point. So we know loss of kinetic energy is given by delta Ke is equal to initial kinetic energy minus final kinetic energy. Let us consider this is equation 1. Loss of kinetic energy is given by this. Where what is initial kinetic energy? What is initial kinetic energy and what is final kinetic energy, you may ask. Initial kinetic energy is kinetic energy of the entire system. Entire system. So let us write it as where initial kinetic energy before collision is equal to, this is at zero, this is at rest, block is at rest, this is only bullet is only moving, so initial kinetic energy is nothing but half mu square. Final kinetic energy is that is after collision. After collision both are moving with the common velocity, so kinetic energy is nothing but half small m plus capital M into common velocity square, where common velocity is what, again here you can write directly, because common velocity is nothing but, by using law of conservation of momentum, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2, we get v is equal to what, m u plus momentum of the block was zero, initial momentum, so divided by total mass, m plus capital M will give you v, and substituting this you will get kef, final kinetic energy. This implies kef is equal to half into m plus m plus capital M into v square. V is this, so square of this is m square u square by small m plus capital M whole square. Guys, I hope you are following this. Okay, I hope you are following this. So m plus m gets cancelled, then you will get final kinetic energy as, this implies final kinetic energy kef is equal to half into uh, m square by m plus capital M into u square. This is final kinetic energy. Let us consider this is 2, this is 3, this is 3, and substitute it here, guys, substitute here, then you will get the loss of kinetic energy, loss of kinetic energy. But sometimes you will ask to find the initial kinetic energy in terms of the what is that, you may ask to find this velocity of the bullet, so that it has to raise to some height, known height. In such cases we have to deal in a different way, that we'll see. First let us try to finish this loss of kinetic energy part. So this implies loss of kinetic energy is delta Ke is equal to half m u square minus half into m square by small m plus capital M into u square. Here half is common, m, of course m is also common, u square is also common. If you take this out, half m u square, and simplify, you will get a different relation. What is that? Half m u square, if you take out, you will get 1 minus 1 m will be remaining here, m by m plus capital M. This on simplifying further, what you will get, guys? Look here. So this is equal to cross multiply, you will get m plus m minus m, small m gets cancelled, you will get capital M. So you will get loss of kinetic energy is equal to, therefore right, half into small m capital M divided by small m plus capital M into u square. This will be the loss of kinetic energy in case of ballistic pendulum. Ballistic pendulum. Okay, fine. But sometimes in this you may ask to find few more points. Like what is the initial velocity, what is the initial velocity required to give to the bullet, so that so that it raises to some height, it raises to a height of h, you may ask to find. In such cases, in such cases you have to or it has to raise to a height h, you may ask to find out this kind of questions. You have to use the what you call the concept of law of conservation of energy, and you have to deal after collision case. After collision law, you have to apply law of conservation of energy after collision. Okay, so let us see what is that. To find the even final velocity in terms of height, or initial velocity in terms of uh, height, or in some let us see. So to find in case of ballistic pendulum only, to find v and u in terms of h, to find v and u in terms of h. By this time you should be having clear idea about what is v and what is u means. U is initial velocity given to the bullet and v is common velocity after collision. That's it. Okay, so for that purpose let us try to apply law of conservation of energy to the system after collision. So we can say from law of conservation of energy, you can say after collision. Okay, okay guys, after collision, after collision, from law of conservation of energy, you can say from this diagram, just after collision these two will stick together and moving with some velocity v. With this velocity, they're having velocity means they're moving with some kinetic energy. With this kinetic energy they have moved ray and raise it to this and stop. This entire block will stop. Then again try to undergo oscillatory motion. In this point, you can say that entire kinetic energy will be converted into potential energy after raising this to height. After raising this height, that means kinetic energy here is equal to potential energy here. So by equating them, or from law of conservation of energy, you can give some names to these points. This is point A. This is point B. So we can say from law of conservation of energy, total energy at A should be equal to total energy at B. Here total energy at A is nothing but kinetic energy only. So we can say this implies here total energy at A is half into mass of mv square. Mass is m plus m into common velocity square is equal to, at this point B, potential energy is 0 because that level will be considered as the reference level. At B, the entire kinetic energy converts into potential energy, so it is equal to mgh. It is equal to, total energy will be just only potential energy. It is nothing but m. My m is nothing but small m plus capital M into g into h. Now here m plus m gets cancelled, and this 2 if you send here, and then you can write v is equal to square root of 2gh irrespective of its mass. The velocity, common velocity in terms of height raised is this. Common velocity is given means you can write h is equal to v square by 2g, or you can also see sometimes h is equal to v square by 2g. If you know the common velocity after collision, by using this you can calculate the height raised by using this relation. Okay, whereas how to express the initial velocity in terms of the height raised? From here, if you observe this uh, from this what do you call it, by applying here you have expressed this common velocity, right? From this only we can find that. So from law of conservation of energy also we know that v is equal to what? Common velocity mu by m plus m m. From this implies you can say small u is equal to m plus m divided by m into v. So m plus m into v by mu, right? Or by small m if you want to u. So here this v can be expressed in this way in terms of height, and hence you can get u in terms of h. So it is equal to small m plus capital M by small m into V is square root of 2gh. So therefore you can write this implies U can be expressed as U is equal to, so you can express, you know how to express final velocity in terms of height raised or height in terms of this, whereas you can also express U is equal to m plus capital M by small m into square root of 2gh. So all these expressions you have to remember, guys. Okay, fine. These are few things you just need to have an idea. Now let us try to work out some questions related to these points. So level 2 exercise 2. Do you have any questions there? Let us see. Level 2 exercise 2, I think we have completed all the questions based on this. Open your volumes. Yeah, I think based on elastic and inelastic collisions in level 2 we have completed all the questions. Next, level 2 exercise 1. Level 2 exercise 1. Yeah, based on elastic and inelastic collisions. Based on elastic and inelastic collisions, I think here also we have completed this. Right. In yesterday's study hour, we have discussed a few more. So this also we have completed. Next, level 1 exercise 2. Let us see. Level 1 exercise 2. Level 1 exercise 2. Here there are some questions. Yeah. See here, question number 44. If you see from these questions, let us see. The question is, a truck of mass 15 ton moving mass, write down this question number, you can say 44. If the question number changes, try to go through the question carefully and refer that one. Okay. A truck of mass 15 ton having moving with 1 meter per second, collides with a stationary truck of mass 10 tons. 10 tons. Okay. And automatically connected to move together, then the common velocity is. Yes, guys. So you should remember simply what is that? What do you call common velocity? Perfectly inelastic collision. This is something like perfectly inelastic collision. So what is given here? A truck. You can consider this as first M1, first mass. M1 is equal to 15 ton. 1 ton is equal to how many kgs? 1000 kgs. So 15,000 kgs. Okay, and it is moving with the velocity of, you can say initial velocity u1 is equal to 1 meter per second, and it goes and collides with a stationary truck. Stationary means the second body which is at rest, whose mass m2 is equal to stationary truck of mass 10 ton. 10 ton, so it can be expressed as 10,000